Like he said, my name is Destiny Anyaiwe, and this is a talk on Alzheimer's disease. It's going to be a little bit of research, play, and learning. Okay. So we begin with the play, which is like watch a movie, but it's not a good movie, I must warn you.
The state at the epicenter of the Alzheimer's epidemic is Florida. There are at least 500,000 patients here, and the number of people at risk increases every year. We have the highest number of 60-plus adults in the country, and our population is just expanding like never before.
When you put forward the simple mathematics of dementia and Alzheimer's patients, we're looking at as many as 750,000 Alzheimer's patients in the next 15 years.
One of those patients is Phyllis Shannon.
It's in the hospital, so I've been visiting this sick.
She's 89, and she lives outside of town.
And I get on my car, please.
I don't think you have a car anymore, Grandma.
What happened to it?
I think the engine blew up.
Oh, really?
Mom has been unpredictable. It's probably an understatement. Probably goes back 5-10 years. I think we started noticing the repeating every, that sounds like 10 minutes. She'd come back and ask the same question.
My car's out in the garage, isn't it?
No, you don't have a car anymore. The engine blew up.
When did that happen?
Oh, a while ago.
See, but more recently, it's been, I think, a minute.
Where's my car?
In the room.
Mom? You want to start over here? Just like people.
How can a losing person in this house?
Phyllis has been living alone since her husband Dick died, 7 months.
Mom, that's all right, come on. The time that it's really hit me as far as her condition, a lot of it was after Dad died. Well, it's probably right in front of us, so somewhere.
Maybe it's in the car.
Sometimes she'll go, oh, yes, Dick's gone, he's dead. And then in the next breath, she'll go, I gotta go check on Dick. He's been in bed all day, he's sick, and I'm feeling good. How many places have you got to go?
To see Dick.
Okay. Where else?
That's all.
Yeah. More recently, she informed me that Dad was over there in the park, and he was going fishing. So I said, Mom, no, he's not. So I turned my back, gone into the house for something, came out, and she was gone.
Phyllis left the house and walked several blocks looking for her husband. Rick found her near the edge of the lake in a secluded park.
I was between frantic with her taking off and getting upset. There's gators over there in that park. There's, I'm not going to say goons, but there's other characters over there that hang out in the park. She could easily got hurt. And he alone could have her trip and fall, and there's nobody around. The worst part was some weeks ago, we had some leftovers for her to eat later. Came into the house and it was all smoke. I mean, just like, what the heck is she doing? Go into the kitchen and there's a paper plate next to the sink with the chicken on top of it, and the paper plate is burnt. What'd you do? I tried to heat up the chicken on a boil.
Rick took the fuses out of Phyllis's stove and microwave. But the fire made him realize that it's really not possible for her to live alone any longer.
My dad was still alive. One of the things that he wanted more than anything was go on and stay in that house for till she passed. We've tried, but as much as I'd love to be able to honor him with that wish, it's just I can't.
Daisy Duarte spends almost every moment of every day taking care of her mother, Sonia. We go over and I wait Alzheimer's it's a horrible way to be. No, it hurts to see someone that's open, someone trying to raise 3 kids. The state at the
All right. The volume is poor. We could have had more fun. So, but I guess we all get the idea. And the worst part of it is not only the patient is suffering this disease, the caregiver, the family members, those neighbors, everyone is suffering from that one person who has that disease. So it is a practical problem that needs practical solution. I could also share the video with you if you really want to finish the video. But because how poor the audio is, let's start. The first thing that comes to mind is when I forget where I keep my key, or when I forgot to keep a date, does that mean I have Alzheimer's disease? The quick answer is no, all right? So that we all get happier and calm yourself down. But it could be an indication. It couldn't even be, it could be as a result of emotional problems. You're thinking about something too much. It could be as a result of some medications you're currently taking. Okay, it could be kind of stress you're going through. But aging does not necessarily mean one has dementia. In fact, science has proven that dementia, even before it starts exhibiting its, before it starts manifesting, the patient has been suffering silently for over 30 years or more. Okay. So here we have a little bit of this normal aging and then Alzheimer's disease. I forgot to pay my bill for last month. Oh, this is second of the month I've yet to pay my bill. That is okay. I don't know what month is it or what day is it. Just occasionally, that is okay. But when your personality changes, a total change in your personality, then it begins to become a cause for worry. Under the hood, what happens? What gives rise to this situation? I like to think of our brains or our neural system like a traffic, maybe because of where I am, where I come from. I'm from Nigeria, where people don't know how to drive. Yes, this is a typical day in Lagos State. So everyone wants to go out or go to a particular destination, but we are all here 2 hours, 3 hours in this sort of situation. Now, going back to Alzheimer's disease and our neurons, think about it as each of these cars are carrying a particular message from one point to another, but they are all jammed here. So the transmission is stopped, the communication is stopped, everything is just jam-packed, and they are all here doing nothing. And that is what happens when one has Alzheimer's disease. We have different reasons. One of them is the genetic, called a polypopal gene that is responsible, or those who have, or it is sort of assumed that those who have this gene hereditary are prone to develop the disease, or the only early onset of the disease. But also other research has also shown that this is not always so. Protein factors, there are amyloid protein. These guys form like a plaque in the brain, sort of disturbing the communication, or tangles. So tangle the brain, this is the tau protein, forms tangles, such that communication, just like the traffic, is blocked because the neurons can't move to transmit these informations. Lifestyle, smoking could also have kind of effect. Different, maybe sleeping less. Okay, all this could be, over time, could lead to this sort of jam-packed neural communication. Environmental factors, where you live, you are exposed to even bad air or things like that could also sort of, you deoxidize, anything that deoxidizes the ions or neurons in the brain is an agent to cause any of this sort of traffic jam, which could reduce communication or sometimes even bar communication. And that is where the Alzheimer's disease starts from. Apart from that, another life expectancy is increasing. All right, life expectancy is increasing. As life expectancy is increasing, this number of stress or the level of stress the human body can contain is only but limited. So if life expectancy is increasing and one has maybe, a human has maybe 100% ability to bear some kind of pains and stress, when you go beyond the life expectancy, you are expected or you're hit by maybe 120% of stress. So at the end of the day, the body will give way, giving rise to Alzheimer's disease. So this is a trend. In Canada, in 2016, is 82 years was the life expectancy. In United Kingdom, 80, America, 78.69%. In 2019, there's a rise from 0.69 to 0.87 in America. So as this keeps rising, we expect that more persons with Alzheimer's disease, the number of persons with Alzheimer's disease will increase because of the life expectancy. All right, so that said, we need to find, so you could find a cure maybe from the medical approach or biological, neurological, medical, and then my area, bioinformatics. So for the biological approach, they want to think about how can we stop the tau proteins from tangling? How can we stop the plaques from the protein to plaque up? For the neurological ones, they want to talk about neuroimaging. That's another new area that's interesting right now. In fact, this image is from neuroimaging. And they want to find out how does the apolipoprotein protein behave and how can we sort of handle it and play with it for a better result. So medical, do we want to reduce the particular medications, one type of medication, or increase another type of medication? Those are areas people are looking at to solve this problem. From our own angle, or my own angle of bioinformatics, we want to see how we can write programs to be able to classify and predict or probably use for diagnosis. The worst thing, and probably what I did not mention, is that there's no cure for this disease. So because there's no cure for this disease, for me personally, I prefer the act of preventing it. So and I'm working towards how can we find out when this thing is about to start or early onset so that medications could be administered at that time. We all know that one cannot be treated for a disease yet to be diagnosed. So it is better we can send out signals or look for signals that we'll be able to use to pinpoint when this disease is about to start or early onset of it. So from my bioinformatics point of view, what I do is to, first of all, model the problem and look for how to collect data that's in line with the model I've created, and now analyze that the data using programs or computer programming. One such data is spectrometer data. A slice is what we are seeing now. A slice of such data is what we see. So you could have mass spectrometer data could come from saliva, analysis of saliva, analysis of blood, or what they call it serum, or urine. Upon analysis, you get these results with these features here, where this is the mass to charge ratio. This is the ion mass, means the number of ions present in the analysis done. The signal to noise ratio, the peak type, Substance mass, the saliva, remaining saliva, for instance, or blood or urine. And then the time of flight intensity. The time of flight intensity is the time it takes each of these ions to travel through the mass spectrometer chamber. And then the peak type is when it's traveling, does it sort of break down further? If it doesn't break down further, then means that peak type is first pass. But if it breaks down along the chamber, it breaks down further, becomes second pass. But if at the end of the analysis we don't have the second pass or first pass recorded, we now have we now indicate estimated pass. The signal to noise ratio is like kind of entropy in that chamber as the ion is traveling. Maybe the number of collisions that it encounters and things like that. Okay. So we have a lot of slides. Each of them, so a particular analysis could give rise to about 500 rows of information or ions. So each of these are ion 1, ion 2, so on. So we could have 400 ions in a particular analysis, or even depending on how good the analysis was, or those that are differentially expressed, uniquely expressed. So sometimes you could go down to about 222 rows of ions for analysis. So this is one of the models I created. In this case, I'm looking for the data we just saw, so unclassified data. And this unclassified data is assumed. It's a supervised learning. So unclassified data from people we already know their health status. So if it is a normal person, someone with mild cognitive impairment, or someone actually suffering from the disease, we already know. But when we are doing the training, it's kind of you put it in the black box to find out the results and see if the result from the black box corresponds to the result in reality. So the model goes like this: unclassified data points. So you put it into a particular model, maybe a program. So in this case, I'll have to diagnose or classify them. So you have to learn from the unclassified, you have to learn them to classify them. After the classification, I'll try to see if I can predict. So I put it in another system called the fuzzy criteria, and then I come out to find out if that person is an incipient case or a relapse case. In this relapse case means the guy doesn't have the disease. The incipient case, there's a possibility, high chances of it's coming up. That's what we mean by it. So one thing in this one of my work is on extended Euclidean k-nearest neighborhood, okay, and weighted Manhattan distance classification. I'll be talking about this one for today. To use the extended Euclidean nearest neighborhood, we had to extend the Euclidean distance as we know. So this is the usual Euclidean distance functions, any of them here. But when we talk about the extended one, we throw in the exponential value to increase the distance. Because we're looking for closest neighborhood. So we're looking for any situation that even when we try to push them apart, those that actually end up still being very close is the ones we select as being differentially expressed. So if I have a mass, let's say this guy, number 1, this is the mass value, and we have another, let's go this way. So I have this, say this is table A, and this is table B, for instance. So you notice that the mass value here and the mass value here are different by 0.02, okay? So what we're saying is, suppose this mass is actually of the difference between mass in A and mass in B is the same. We now want to what? Use, that means the mass value is equal, but we want to pay attention to their time of flight intensity, the strength with which they travel through the chamber. But if the mass values are different, then we want to throw that, we want to also increase their effect apart and then see if that will sort of give us a close relationship by using the exponential function. So this model is what we call the extended k nearest neighborhood. And by this, we compare, if at the end of this analysis, they still remain close, we look for the closest guys to collect and say those guys are alike. If they are not close together, that means they don't have anything in common. So just by the word nearest neighborhood. Okay. So if we do that, for every ions, maybe 400 ions in a particular sample, we compare it to every other ions, every other results we have in that pool of results. At the end of the day, the final decision is made by majority vote. So the closest of all, those ions are closest to MCI. How many ions are closest to MCI? How many ions are closest to those with treatment for Alzheimer's? And then control guys. By vote, here I can now see that the test sample tested belongs to the mild cognitive impaired. And then by majority of vote again, the second sample tested belongs to TAD, meaning it's for Alzheimer's disease. So by this, we are saying that this test belongs to MCI, and then, which is mild cognitive impaired, and this test too belongs to this. So we keep on testing all that for all the pools, the elements we have in our pool, and then we come up with this percentage of performance. Though I did not mention that we have, before, I don't do that part, I don't know anything about that part, but when they take the samples and they treat those samples or analyze those samples, they do it with, let's call it a plate. There's one plate called CM10, there's another plate called IMAC30, there's another plate called Q10. So this is how they supply the sample to the mass spectrometer machine, all right? So those of them that was sampled using CM10 plate, the highest was 88% performance. For IMAC30, the best for the high, they do that for low energy and high energy, and then the best was 87, and the Q10 was 90. Overall, we see that even for the low and high intensity energies, the Q10 performed better. Because of this, every analysis we're going to do now will be based on this plate, Q10. So by Q10, what we mean that we had 20 control sample elements or ions that we want, results that we want to classify into being normal, mild, or Alzheimer's patient. And we ended up having 19 of them actually classified correctly. And then 18 of TAD actually classified correctly. And that was the distribution that gave rise to this 90%. So overall, we sort of made a plot to make it a little bit better, more attractive, and this is our result for this classification. Okay. So remember, so now we have put in unclassified data. We have classified it using the extended k-nearest neighborhood, and we have this data classified. Now we want to see if they are incipient case, if we can predict with that data. To predict, we come up with this simple formula, where C is dose for control, T is for TAD, those that actually have the disease, and N is the total number of ions in each sample result, like 420 or 222, depending on those ions that were uniquely expressed in the particular result you are dealing with. Okay, so we do that, and that when you do this, you compare, you take the maximum to be, the result of this analysis or this fuzzy criteria is to say, okay, if this is higher, then this becomes your opinion. If this is lower or this is higher, this becomes our opinion, the maximum of any of those two. So we did that. We had 20, if you remember, we had 20 sample cases. Each of these 20 had about 420 ions in each of these results. So we have these 20 samples to deal with. The first case, the number of ions, okay, in this analysis, we decided to say, okay, those of the TADs and mild cognitive impaired guys we took all of them to be under TAD. And then control remained control. So in this case, we're able to analyze that or count, or those nearest ions nearest in this result. The total now, if you check it out, the total is about 190 something, 299, I guess so. So these 299 ions in this result we're dealing with, 123 of them counted for control, while 179 counted for TAD, which when we now use this formula, this guy is higher. So we can now remark as incipient. Okay. So we do that for every ion for every result, or for every ion in these results, all these results, and we came up with this chart. One thing that was very, very interesting was that while we were working, the guys from Beaumont Hospital called to say, okay, there's an issue that these guys, 4 of these ions, were wrongly classified to be mild cognitive impaired, but they were originally controlled. And we ran back to this result, and we saw that our analysis actually proved them to be CON. We can see that the rate with which they indicate, using this mass fuzzy criteria, the rate or the potential or their potency is far, far higher than any other distribution. So which sort of gave us a reason to laugh and be happy with the work we have also actually done. So with this, we could predict. So by swap of a saliva or check of blood, analysis of a blood sample or urine, we could throw this into this model to be able to predict, to know if there's an incipient case of Alzheimer's disease or the guy is good to go. So as we begin to wrap up, I want to, a few slides to just talk about the news on Alzheimer's disease. So other guys are working. I think Bill Gates' father or mom, I think, so has this disease. So he just donated about $100 million, something of that nature, to Alzheimer's research. Apart from that news, these are some current news. There's this hyperbaric oxygen chamber for taking care of Alzheimer's patients. So what that does is they put the guy or the patient inside this chamber, and they oxidize his system. So those neurons that are still functional but not functioning, so the oxygen gas will sort of revigorate those neurons. So some results have been counted that it's working now. There's a new one. And with this, there's another guy here predicting the disease before memory loss. Because once memory is lost, the whole thing is over. Like I said, there's no cure for the disease. So there's another guy doing that. And then here, these guys are saying, University of California, they are working on pollution as a close cause for Alzheimer's disease. Yesterday, when I Googled news on Alzheimer's, someone is thinking about using lithium, progressive dosage of lithium, as a cure to the disease. So these are some of the few informations that are currently out there, but in all, we just need to prevent it, because they say prevention is better than cure. All right, thank you so much for listening. Questions? Yes, voila.
But I'll let the students go first.
Unfortunately, not today here.
Bruce is supposed to do
The data collection, where did your data for the analysis, where did you get the data from?
From Beaumont Hospital.
From where?
Beaumont Hospital.
And in terms of your model, the accuracy of it, any false positives, false negatives, how accurate is the model?
Yes, the model was like 90% good, so I expect 10% false negative results.
And how many, in terms of your data, how many records did you do this analysis on?
60.
60?
60 of them, yeah. And when we say 60, we say 60 times 400. So each of them is 400.
Right.
Start playing, take away some of them that are not uniquely or differentially expressed. So at the end of the day, I was working with each sample result was about, I had about 222 ions in each result. It's a very big data, but it's not big enough because 60 patients is not enough to classify something. I need more, which is why I hunger to start my own lab here.
Thank you.
You're welcome. Yes.
Yeah, so I wanted to understand a little more of what is needed. So this is, it takes saliva from a patient and that's run through an acid spectrometer and we come up with these two criteria.
Yes.
Can you talk a little more about what that test 1 and test 2 were? Like, I mean, I understand these are probably some sort of black boxes, right?
Yeah. Which one?
Before that, you had two, yeah. So test 1 and test 2, which are identifying either the mild cognitive disorder or
Okay.
right. Well, so that was one question, and a follow-up to that is like I'm guessing that is based on your equation that you wrote before.
This
Right,
this one here?
Yeah. So that's probably based on the previous slide where you had the
Yes.
equation.
Yes.
There, what is equation 1? In the middle, where you,
Okay, the equation, oh, maybe it's a typo, sorry. Oh, I didn't even see that.
so this is just a combination of those two
This,
criteria.
just forget about this.
Right, but so you will have a situation where the masses are not equal as well as the time of flight intensities are not equal.
Yes.
So you will need some combination of those.
Yes.
And is that well known,
So if-
understood?
If it's what?
Is that, is that combination, I mean, just because you know the limiting cases doesn't mean that you may know what happens when both of them are different, right? Some sort of
Okay.
overlap of the two.
Yeah, okay, now your question is, first of all, this is bad, okay? Number one.
That's bad, okay.
Number two,
Okay.
once we have the, why no, Bruce, why no?
No chalk?
No chalk. You don't have a teacher. Okay.
Was there a hiding
Oh,
chalk?
thank you. Thank you. I usually come with my chalk. I never knew this. Thank you so much. Okay, so the usual equation is, say, x squared plus y squared, where this guy is, say, x1 minus x2 squared plus y1 minus y2 all squared. This is the usual Euclidean equation, right?
Oh, so this is Euclidean.
Yes.
Euclidean.
Yes. So once M, A, and MB are equal,
Oh, I get it.
this guy is gone.
I
Okay. All right. That's my
I
job.
missed that it was Euclidean.
Yes, that's my job, to get my students back on track. Okay. So that's it. So answered?
Yes, that's, so now my question was like, how do you go from this to the tests? Like,
Okay,
what are the
good job.
criteria?
Yes, so let's go back a little bit. So here, we have, let's say we have 22 ions, 22 rows. So assume we have 22 rows here, 22 rows for each of these results, right? So I'm making a pool where this is the control guys, where this is, the other one is MCI, and then the other one is the AG guys. Okay? I make a pool. So for each of these ions, for let's say this guy now is my test 1. Okay? For each test, for each result or test 1, for each ion in test 1, I want to find out who is it closest to using this K nearest neighborhood. Then I do it for ion 1, ion 2 to ion 22.
And these are for 22 different patients.
Yes.
Okay.
So
And
this.
then you classify.
Yeah, then I classify. So I now count how many of these ranked MCI, how many of these closest to TAD, how many of these is closer to control. Then I use majority vote. So how many of those ions contained in test 1 is close to control? Containing test 2 is close to MCI. Containing test 1 is close to TAD. Then overall, I use majority vote to come up with my result. Good?
I understand it.
Okay.
But so my question is like, so you basically have some sort of, from this probability will tell you some sort of metric on which one is which.
Yes.
Just given this.
This
equation,
analysis,
right?
yes.
So then my question would be, when you are going to the predictive side, what is the necessity for machine learning? You can just take those parameters and
Throw it in, yes.
throw it in and say.
See the result. I see the
So
result.
there's no learning.
There's no learning per se, apart from this. The
Apart from
machine to learn is just this k-nearest
Yeah,
neighborhood.
this is because this has a lot of data.
Yes. Yes. So that k-nearest neighborhood and the majority of vote is the learning there. Professor Nelson, you want to say?
Alzheimer's is considered to be an elderly disease, but what's the earliest it can onset that they see people?
30s.
10 to 30?
30s. 30.
And is there trends over, because a lot of people argue that it's environmentally triggered. So is there trends of this getting younger and younger throughout the decades?
That is one of the research I probably want to do right now. With regards to sex, geographical location, lifestyle, those kind of demographic. So I don't have an answer for that. Yes.
I already forgot everything you said. Can you give the whole lecture again?
Yes, I can. Maybe next month. If March is free. Okay. More questions for me? None? All right.
No more questions. I give Destiny another.
Thank you, guys. Thank you.